Good day, students. In our previous videos, we have seen about the system parameter definitions of radio frequency system design. Okay, like gain, noise figure, SNR, characteristic impedance, S parameters, okay, impedance matching, average value, RMS value, crest factor. So all these are the parameters which are required for your RF frequency system design. Okay. So from this video onwards, we will be discussing about the elements of digital baseband signaling. So first, before moving on to the elements of digital baseband signaling, we should need to know what is a digital baseband system. So a digital baseband system refers to a communication system in which the signal is transmitted in its original digital form, okay, without modulation onto a carrier frequency over a transmission medium. So the signal is in the original digital form. There is no modulation in that signal. That is called a digital baseband system. So these systems operate in the baseband frequency range. So what is the range of these systems? Is they have the baseband frequency range. What is a baseband frequency range? That means they transmit data using the entire bandwidth from 0 hertz up to a maximum frequency determined by the data rate. Okay, so always start from 0 hertz till the maximum frequency. That is a digital baseband system. So we have some components of digital baseband system. What are the components of a digital baseband system? We have a source encoder. Okay, so usually we know what does an encoder does. So an encoder converts the input data, for example, text or audio, okay, into a digital bit stream. So that's the work of an encoder, right? So here our source encoder converts the input data into a digital bit stream, okay, and it uses some compression techniques to reduce the redundancy in it. Then second one is our channel encoder. Okay, so channel encoder, it performs error detection and correction bits. Okay, so it uses Hamming code, turbo code, all this, and performs the error detection and correction. Okay, then we have the line coding, which converts the bit stream into a signal suitable for transmission over the channel. Okay, so we have the bit stream now. That bit stream is converted into a signal. So that is where your line coding comes into scenario. So for this, we have various line coding techniques. Okay, like non-return to zero, NRZ, and RZ, return to zero line coding, and Manchester coding. All these are line coding techniques. And the fourth component of our digital baseband system would be a transmission medium, okay, which is a channel. So medium is always called as a channel. So physical medium like copper wires, optical fiber, or wireless. So these can be one of the medium, okay, for your transmission. So like copper wires, optical fiber, or it can be wireless. Okay, so baseband transmission uses the full bandwidth of the channel. So you should know that a baseband system always uses the full bandwidth of the channel. Then only if you understand this, only you'll come to know the next topic. Okay, here make a note of it. The baseband transmission uses the full bandwidth of the channel. Okay. Then finally, you have a destination decoder, which converts the digital data back to the original format, which is called as decoding. So once to reach the receiver, you need the original message, right? So the original message is, which is converted the digital data back to the original message format. So this is about this is digital baseband signaling. Okay. So let's move on to the complex and envelope of band pass signals. Complex envelope of band pass signals. So from now on, we'll be seeing about the elements of digital baseband signaling. The first element would be complex envelope of band pass signals. So before knowing what is the complex envelope of band pass signals, you need to know what is a band pass signal first. Okay, now so far we were discussing baseband signals. Now we should know what is a band pass signal is. Okay. So a band pass signal is a type of signal whose frequency components are confined within a specific range. Okay, whose frequency components are confined to a specific range. Complex envelope of bandpass signals. We are in this topic right now. And here we should know what is a bandpass signal. So a bandpass signal is a type of signal whose frequency components are confined within a specific range between a lower and upper cutoff frequency rather than starting from 0 hertz. Okay, as in baseband signals. That's why I mentioned there, I stressed in baseband signals. In baseband signals, the range starts from 0 hertz, but whereas your band pass signals, it does not start from 0 hertz. It is a specific range between a lower and an upper cutoff frequency. Okay, so it occupies a band of frequencies not centered at 0. Okay, but whereas it has a specific range between lower and upper cutoff frequency. So that is your band pass signal. So we know what is a band pass signal right now. So from this, we will be knowing what is a complex envelope of a band pass signal. So what does the complex envelope mean of a band pass signal? So it is a powerful representation of band pass signals that simplifies their analysis by converting them into a low frequency equivalent. So it gives a low frequency equivalent. That is your complex envelope. Okay. So mainly we use this complex envelope for modulation, demodulation, and signal processing. For all this, it is used. Okay. So it is a key concept in your signal processing for simplifying analysis and demodulation. Okay, so we'll just see the diagrammatic illustrations of what is the complex envelope. Okay, so if you look at this diagram here, this is a band pass signal. Okay, so a band pass signal, as I said, doesn't start from 0 hertz. It starts from a specific range, okay, between upper and lower frequencies. So here we have the lower frequencies F naught, minus del F till minus F naught, where F naught is your carrier frequency. And again, you have the upper frequencies F naught to F naught plus del F. So this is your band pass signal. Okay, so let us consider a Fourier transform x of f of a signal x of t that has the band of frequencies 2W and it is centered about the frequencies plus or minus f naught. Then the signal is called as band pass signal. This is represented here, right? So here your f naught is your carrier frequency. Okay. So before getting to know the envelope of the band pass signal, we need an expression for the pre-envelope of a band pass signal. Okay, so the pre-envelope of a band pass signal is given by this equation. That is x plus of t is equal to x dash of t into e to the power of j 2 pi ft. Okay, so here in this equation, x dash of t is the complex envelope of the signal. X dash of t, which is represented as the complex envelope signal. So in the next page, we'll see about the exact diagrams of the band pass signal, what is a pre-envelope and a complex envelope. Okay, so this figure shows the band pass signal as shown here. Okay, same like this, only the shape is different, right? Okay, so you have the amplitude spectrum, okay, and it's divided into two bandwidths, that is 2W and 2W, lower cutoff frequency and upper frequency. This is your band pass signal. So it's not starting from 0 hertz, right? So this is a band pass signal. The pre-envelope of a band pass signal is shown here in this diagram, which is B. So the pre-envelope covers only the upper cutoff frequencies, right? There it divides into F naught minus W and F naught plus W. Okay, so and your carrier frequency comes in the center. So that is your pre-envelope. And from this pre-envelope, if you take the Fourier transform, okay, you get the complex envelope. And by using the frequency shifting property of the Fourier transform, we can find that the spectrum of the complex envelope x dash of t, okay, is limited to the band minus W to W. So this is your complex envelope of a band pass signal. So I hope you're clear with what is a band pass signal is and the complex envelope of a band pass signal. So for now, in this unit, the basic understanding will be sufficient. In the next further units, we'll be going into detailed derivations. So for now, you should have a knowledge about what is a baseband signal, a band pass signal, and the complex envelope of a band pass signal. Clear? So in the next video, we will see about sampling, jitter, and other few elements of the baseband signal. Thank you.